All right, welcome to our week 4 lecture 3 on one sample t-tests. So when do you use one sample t-tests? Well, you use them to compare the mean of one sample, and the sample mean is represented by a little X bar, to some real or hypothetical population mean, that is a mu, that's the Greek letter for mu, when the dV is measured on an interval or ratio scale. So you only got one sample, you got a dV that is on an interval or ratio scale, and you want to know, does this differ from some hypothetical average? So for example, does the temperature of 130 healthy patients collected during doctor visits differ from the hypothetical population average of 98.6 degrees? So you've heard that the average body temperature is 98.6. So they collect body temps for 130 folks who are healthy, and they say, does this differ on average from this hypothetical 98.6? One sample. How about does the average NEO-PI neuroticism score for a sample of veterans in treatment for PTSD is compared to the population normed age-sex mean to see if they are more neurotic on average? So get the sample of vets, get their neuroticism score, and you want to compare it to on average, what would be expected for their neuroticism score given their age and sex. Again, one sample dV is interval or ratio. On average, the benefits at a company are supposed to be the equivalent of 17% of the employee gross salary. So the folks in HR, for each employee, calculate the percent of gross salary represented by their benefits, and they average that across all their employees to see if it differs from 17%, the expected population value. You got one sample compared to 17%, the expected population mean, and that is a one sample T. So this one's a little interesting, this particular test, because it actually comes from beer. So students' tea comes from Guinness, actually. So it turns out that the one sample tea was invented by this guy, William Gossett, in 1908, when they had to do stats by hand. He was working as a brewer for Guinness in Dublin, and he wanted to compare the quality of batches of barley to some expected average. He invented this test, just for fun, because there wasn't TV back then, or YouTube, I guess. So he had to publish it under a pseudonym, Student, because of, when you work for a company, they own everything you make, right? So that's why it's called Student's Tea. So fun fact of the day. It has certain statistical assumptions. So remember those, all the parametric tests have these things called assumptions. So it makes them parametric tests that if they have to be true in order for the test to work properly. That is, to get you the right result. What are the assumptions, the things that should be true for one sample T? Well, first one is normality. So that is the sample of scores is drawn from a population that has normally distributed dV values. So how do we test that, or how do we really look at that? Are the scores normally distributed? So we look at the skewness coefficient. The second one is the sample standard deviation that is based on your little sample is a good approximation of the population standard deviation. It's used to estimate it in the equation, so that's why. It's just sort of an assumption. Should be true for this to work. So to write the hypotheses, we are comparing a sample mean to a population mean now. So you can have one or two-tailed hypotheses, but SPSS only calculates two-tailed significances, but don't you fret. You can get a one-tailed significance by just dividing the sig that SPSS gives you in half, divide by 2. So for example, if it gives you a sig two-tailed of 0.04, sig one-tailed would be 0.04 divided by 2, you get 0.02. So it's not a big deal at all. So two-tailed hypotheses, the way you would write these is that you believe the sample mean will differ from the hypothetical population mean. You're just saying it's going to differ. Not it's going to be higher, not that it's going to be lower, it's just going to differ. So just like a correlation, either way you write, so it's two-tailed. So the way you write that is the relationship between x bar, the sample mean, and mu, the population mean. So if we think that the sample mean is just not going to be the same as the population mean, it will differ, we would hypothesize for our alternative that it would be not equal, right? So what's our null then? Our null hypothesis is where we're wrong. Well, the only case we're wrong is if it's equal. So that's how you write two-tailed hypotheses for one sample t-test. Again, it's always the same, and it's exactly the same actually as correlation if you think about it, two-tailed. So you can also have one-tailed hypotheses, that is where you're picking a direction. So let's say you picked that the sample mean would be higher than the hypothetical population mean, totally reasonable. How would you write that? I think x bars can be bigger than mu, the population mean. Well, you're going to say greater than. I think sample mean will be greater than the population mean. They'll be more or higher. Where are you wrong? Well, you are wrong if you find that they're less than or equal to, right? So guess what? That is your null hypothesis. You are wrong if they're lower than the population mean, or if they're basically the same, given chance. So the other type of one-tailed hypothesis is where you think they're going to be lower, so the sample will be lower than the hypothetical population mean. How do we say we think x bar, the sample mean, will be lower than the population mean? Less than. And where are we wrong? What are the other possibilities? Well, we're wrong if it's equal to the population mean or it's actually greater, right? So this is very similar to correlation hypotheses. If you think about it, this is how you write them for one sample t. So there are decision rules, just like for correlation, for how you reject a null hypothesis. Two-tailed hypotheses, again, you're just saying the sample means can be different from the population parameter or estimate or mean. So there's exactly one criterion that has to be met to fully reject the null, because any difference supports the alternative. That is two-tailed sig. If it's less than 0.05, the difference is statistically significant. You can fully reject the null. If your two-tailed sig is greater than or equal to 0.05, it's not statistically significant. You'll retain the null. That's it. So for one-tailed hypotheses, specifically in this case, we're hypothesizing that the sample mean will be higher than mu. Okay, so they're going to have a higher average. Two criteria have to be met. First of all, it's got to be statistically significant. So again, remember to divide the sig two-tailed by 2 when making this decision. If it's got to be statistically significant, then you want to, so that's piece 1. It is if sig two-tailed divided by 2 is less than 0.05. Okay, there's a real difference here. Is it in the right direction? That's question 2. So is it higher? Because it can be significant because they're lower, right? Which would be not consistent with the research hypotheses. If both these things are true, it's significant and it's higher, you can fully reject the null. If the sample mean is lower than mu, you do not fully reject the null because that wasn't what you hypothesized. It's different. It's lower. That's not what you said. You're wrong. You do not get to fully reject the null. All right. If a sig two-tailed divided by 2 is greater than or equal to 0.05, well, the difference isn't statistically significant. You're also not rejecting the null. Okay. So those two pieces have to be true for you to reject the null hypothesis. What if you hypothesize instead that the sample mean would be lower? It's kind of the same thing, except the direction has to be less than, right? The mean should be lower. So two criteria again, because only lower supports the alternative hypothesis. So you divide two-tailed sig by 2. Is it less than 0.05? If so, cool. There's a difference between the groups. Is it in the right direction? That's part 2. Is it lower? If so, fully reject the null hypothesis. If it's higher, nope, don't get to reject the whole hypothesis because you're wrong. You guessed the wrong direction. Is sig divided by 2 greater than 0.05 or equal to 0.05? Well, then it's not a real difference. You do not get to reject the null. So the measure of effect size for one sample t-test, remember this is your meaningfulness, is eta squared, little n-looking thing squared. And you calculate it using stuff that comes from the formula t squared divided by this sum of t squared plus the degrees of freedom. The degrees of freedom is sample size minus 1. It's on the output. What's it tell you? Well, it tells you the proportion of variability in the dB that's accounted for by being in the sample instead of being in the population, because the IV is a little weird here, right? It's what's the IV in a one sample T? Well, it's the sample being in the sample, not the population. So it's a little weird here. Everything you need comes straight from the SPSS output. So just like with correlation, the R, there is a specific APA way to write up T, one sample T. This is what we call the general form, where we got to fill this stuff out again. And so everything except eta squared, which you got to calculate, t squared again divided by the sum of t squared plus degrees of freedom, comes straight from your SPSS output. All right, well, there's some red crosses on this one. What's going on? We're going to do it. So this isn't that complicated of a test, so that was the entire intro. Let's jump in and do one. Does the temperature of 130 healthy patients collected during doctor visits differ from the hypothetical population average of 98.6 degrees? So it's that example that was on like slide 1. So first of all, is this a two-tailed or a one-tailed hypothesis? We're saying they differ. We're not saying they're hotter. We're not saying they're colder, right? Or higher or lower. We're just saying they differ. So this is a two-tailed hypothesis because we'd be right if they're hotter. We'd be right if they're cooler. So any difference supports the alternative. So we got to write our hypotheses. So I start with the alternative. How do we think the sample mean is going to compare to 98.6? Well, two-tailed, we think it's going to differ. Right? So how do we write these two-tailed ones? Well, not equal to. So where are we wrong? Equal to. Right? That's where we'd be wrong. So that's how you write your hypotheses. Here's what the data look like in the file. There's a bunch of stuff in there happens, but we only use body temperature, that first column, when we compare it to 98.6 degrees. So let's actually run it in SPSS. We go to Analyze Compare Means One Sample T. You get this little box, and what have we done here? We've thrown body temperature in the box on the right. Other thing we had to do was see where it says test value. We actually put 98.6 in there. I think the default's 0. We want to know if the sample differs from 98.6. So here is the sample mean compared to mu. This is what you get on the SPSS output when you click OK. This is what it looks like. What do we got here? A bunch of stuff. So first thing is one sample statistics. You get the sample size, 130, standard deviation, the mean, standard error, whatever that is. But the average body temperature of the sample was 98.249, so 98.2 degrees. The next table there is a one sample t-test table. It shows you up top what value you're comparing to as the hypothetical population value is 98.6 degrees. You get something called the mean difference in there. That's how much the sample mean differed from the population mean. So it's literally sample mean 98.249 minus 98.6. You get negative 0.3508. That is, they're about 0.35 degrees lower body temperature on average compared to what was expected. So the question is that a real difference? Is that just is that a big enough difference for us to say, yeah, that's unlikely to happen if their real body temperature is 98.6? Well, that's why we do the test. So alternatively, is it just, a minor deviation, a couple extra marshmallows in your bowl of Lucky Charms, or is it a real difference? There's our test. So you get a T, you get a degrees of freedom, and you get your sig two-tailed. And yeah, we're going to reject the null hypothesis, aren't we? So 0.000 is less than 0.05. It's two-tailed, so we didn't have to divide it by 2. And so what's that tell us? We're very unlikely to get an average body temperature of 98.2 degrees if the average body temperature of people is actually 98.6. So that is a real difference. On average, the body temperature of the sample is 0.35 degrees lower than 98.6. They are cooler. So you get, even though it was a two-tailed hypothesis, you do get to reach the conclusion saying, yeah, look, they're cooler. This is, again, the what do you tell grandma? Yeah, people's body temperature is actually not 98.6 on average. It's a little lower. The measure of effect size, again, eta squared. How do we calculate it? Well, all the stuff's kind of here on the output. We just got to figure out where to get it. That's the formula. I've filled it out here. We get 0.817 turned into percent just for discussion. It's 18.7% of the variability in body temperature is accounted for by being in the sample versus the population. Where does it come from? So T came from there. So remember, don't forget to square it. There is our degrees of freedom. And our APA notation, finally, remember the way you write it up in APA. You got to fill this thing in with the stuff from the table. Boom, there it is. Where does it come from? There's our degrees of freedom. There's our T value. We put P less than 0.05 because sig was less than 0.05. And our eta squared came from up above, 0.19 rounded to 2 decimals. And that's kind of it. That is one sample T. Good luck.